All right, everybody. Welcome to Lesson 7 of Calculus 2, Partial Fractions, Part 1. In today's video, I'm going to introduce a new technique of integration, which is using partial fractions to split up rational functions, and then maybe we can integrate them more easily. Bear with me here. I don't have you guys tell me to push up the page, so hopefully I'll be able to keep track of that myself. But yeah, here goes nothing. All right, anyways, so what is a rational function, just in case we've forgotten what that is? A rational function ends up being a polynomial divided by another polynomial. You've probably heard this term before. So for example, one rational function we might consider would be something like x over x squared plus 1. We have a polynomial on the top, we have a polynomial on the bottom. So this would be an example of a rational function. Now, what we're going to focus on today is we're going to learn how to integrate rational functions. So if we take this one, for example, we actually already know how to integrate this one. So for this one right here, if we were to do u is x squared plus 1, and du ends up being 2x dx, then if we divide by 2 and have 1/2 du, then our integral will end up turning into 1/2 du over u, which will turn into natural log. So this is one we already know how to do. We could also use trig sub to integrate rational functions. Like for example, if we have, let's say 1 over 1 minus 9x squared. I think this one might be familiar if you attempted the trig sub homework. This is one that we can do via trig sub. We can do 3x is sine of theta, and then turn this into a trig integral that we can do. So we already know how to do this one. We know how to do something like this. But what if we get something that looks like this? Let's say we have x squared minus 1 over x squared minus x minus 6. Now, I guess in theory, we could complete the square on the bottom, although that'll get pretty ugly right off the bat. And I guess we could FOIL out some trig functions on top here. But that would be, yeah, that would not be a great way of doing this integral. So what we're going to learn today is a way of dealing with rational functions more generally. And we're going to use an algebraic technique called partial fractions. So kind of like completing the square that we talked about a few lessons ago, partial fractions is actually just an algebra technique. So we can use it in more instances than just doing integrals like we have here. In fact, we're actually going to use it in another occasion in the course that has nothing to do with integrals. But for the time being, it's just going to be an algebraic technique that's going to help us. Now, before we can learn about that, partial fractions, the technique I'm going to teach you, only works if the numerator of our rational function has a lower degree than the denominator. And unfortunately, this isn't the case for this one right here. So how do we fix that? Well, we can dig up another algebra technique called polynomial long division. I'm sure you guys learned that at some point, but pretty much it's a way to divide polynomials and then have a quotient and a remainder. So we could rewrite this to look like something else. So let's kind of have a refresher. Let's use long division to divide x squared minus 1 by x squared minus x minus 6. All right, so just like long division with actual numbers, we draw this little symbol right here with these lines, and then the thing being divided into goes under this square or the rectangle, and the thing dividing into this will go on the outside over here. Now what we're going to do, well, actually one thing I like to do is I like to kind of offer placeholders for missing powers of x. So I'm technically going to have x squared minus 0x minus 1. You don't technically need to do this, but it does make things a little bit more organized. All right, so then what I'm going to do here is I'm going to multiply this by something that will make the x squared be the same as the first term in here, which is also x squared. But obviously x squared already is x squared, so that something would be 1. So again, I want to find something to multiply by this to get whatever that is. So then I multiply the whole thing by whatever I chose here, which was 1. So if I multiply by 1, I get all of this stuff. And then just like with regular long division, once I do that, I subtract everything I have here. So I have x squared minus x squared. By design, these guys should end up canceling out. We have 0 there. We have no x's minus a negative x. That's actually going to give us a positive x. And then we have -1 minus -6. That's going to give us 5. So we end up with x plus 5 once we're done with this. Now, when we get to the point where the degree of this is lower than the degree of this polynomial, then we're done. And whatever ends up here is going to be called our remainder. And whatever ends up here is going to end up going outside on its own. It's not going to be divided by this anymore. But the remainder couldn't quite escape that fate, so it's still going to be divided by this. So because of this long division, we can end up rewriting this integral we had a second ago, squared minus 1 over x squared minus x minus 6. We can rewrite that as the integral of whatever is up here, so 1, and then we can add in the remainder, is x plus 5, and then we divide by x squared minus x minus 6. And then now our objective is complete. Notice the degree of the top will always be less than the bottom as long as we did our long division right. Now, some of you may have also learned about synthetic division back in your algebra class, and that's really nice if you're dividing by like a single, a 1 degree polynomial. But if you're dividing by quadratics, long division is definitely the way to go here. All right, so normally I would give you guys some practice to work on, but we're not in a live class, so I'll just do the practice for you. So our practice problem 1 is use long division. Practice 1. Use long division to divide x squared plus 5x plus 6. We want to divide that, meaning it's going in here, by x squared minus 3x minus 4. Let's do another example of long division here. So once again, so my goal starting out is I want to find something to multiply by this to get the first term in here. But once again, it's also just an x squared, so once again, we're going to have 1. Just to give an alternative example, if this were, say, like an x cubed here, I would need to multiply this by x to get that. So I'd put an x here, but they're the same thing, so it's 1. So I do x squared minus 3x minus 4 times the thing up here, which is 1, and then I subtract. So I have x squared minus x squared. Those will always cancel if we did this right. We have 5x minus negative 3x, which will actually give us 8x. Don't forget that it's subtracting all of this. And then we have 6 minus negative 4, which will end up being 10. So that means that this division will end up giving us 1 plus 8x plus 10 divided by this. So whatever ends up in the remainder down here, it's still going to be divided by whatever our divisor is over here. Okay, so that's just some practice with long division here. Let's keep going. So what I want to do is I want to use the long division result that I had just a moment ago to teach you guys the technique of partial fractions. So remember, my first problem that I said would be difficult otherwise would be to integrate this, x squared minus 1 over x squared minus x minus 6. And now I'm going to teach you a better way of doing this rather than a nasty trig sub. So what I'm going to do first is I'm going to do long division. And we already did that. We already saw what happened with that up here. So we already saw that if I did long division, it turns into this. So I'm going to write that here. Plus 5 over x squared minus x minus 6. Okay, that's great. And we don't need to be in Calc 2 to know how to integrate this part. This is actually just going to end up being an x. So what we could do is we could really just focus on this integral right here. Now, the first thing we should do is we should try to factor everything as far down as possible. So if possible, try to write everything as quadratics or linear terms. Now this guy, so the top's already a linear term, x plus 5, so we can't do anything with that. But if we look at the bottom here, we can see that we could factor this a little bit more. We're going to have, oops, well, we can't forget our x. It's going to be along for the ride. And then we have x plus 5 here. And this bottom, if we look at this, this is going to be x minus 3 times x plus 2. So make sure you brush off your factoring skills because we're going to be doing that quite a bit. Now, what I'm going to do is I'm going to try to split this into 2 separate fractions that are added together. So that's my goal here. I want to split this into two separate fractions. So what I'm going to do is I'm going to take what I have in my integral, and I'm going to try to find a way to write it as a number, which we don't know what number it is yet, so I'm just going to call it a over x minus 3 plus b over x plus 2. Now, why would I want to do this? Well, if I have just this, for example, this is going to integrate to ln of absolute value of x minus 3 and then times some number. And a similar thing will happen here. This will be b times ln of absolute value of x plus 2. So if I can figure out what these numbers could be, then that means I could do this integral much easier. Now, what we're going to do is we're going to talk about the first case of partial fraction decomposition. That's actually what this is called here. This is the partial fraction decomposition. And that's a very long title. So henceforth, these are going to be called PFDs. A PFD is where we split up our rational function into multiple pieces like this. And it depends on what the denominator is. Now, I'm going to say this multiple times throughout the lecture and also next time's lecture, because we're also going to be doing PFD then too. The number of coefficients you should have here should always be the same as the degree of the bottom. So if I were to FOIL this back together, I would end up with x squared. So it's going to be a second degree. And notice how I have two variables. All right, so this is called the partial fraction decomposition. And now we need to figure out what specific numbers a and b will end up being. All right. Let's get some more paper and figure that out. Okay. So the first way we're going to learn how to do partial fraction decompositions. There we go. That's why I call them PFDs. I don't want to use big words. The first case that we're going to have is when we have distinct linear factors in the denominator. So that's exactly what happened here. Once I fully factor this, I was able to get x plus or minus something times x plus or minus something. I don't get any x squareds down here, and I don't have something like x plus 2 quantity squared either. I just have linear factors, and it's always x plus or minus a different number. That's going to be our case 1 here. And when we have case 1, we're going to figure out a and b using a method called the cover-up method. This is a really easy way of computing the a and b right here. All right, so let's say I wanted to figure out a, for example. Let's say I wanted to know what my a is going to end up equaling. Well, what I can do is I can see what x value makes the bottom of that be 0. And in this case, x equals 3 is going to be my x value. Then what I do once I figure that out is I look at my rational function and I plug in x equals 3 into this. But the problem is you might notice like, oh, if I plug 3 down there, I'm going to get 0. Well, the thing is you plug it into every term except for that one. So that's why it's called the cover-up method. So we take the rational function, we sort of cover up the term that we're sharing with our coefficient here, and then we plug in that number to the rest of it. So if I plug in 3 here, I'm going to get 3 plus 5 will be 8. And then down here, I'm going to have 3 plus 2, that'll be 5. And voila, that ends up giving me my a. My a value is going to be 8/5 for this one. All right, so what we're going to do now is we're going to try to use the same technique to get our b. So what's the x value is going to make that be 0? X is -2. Okay, and we're going to plug that into x plus 5 over x minus 3. And we're going to skip the x plus 2, or we're going to cover it up because -2 would make that 0, and that'd be an issue. So if I put -2 into here, -2 and 5 ends up being 3. -2 minus 3 is -5. So my b ends up being -3/5. All right, so what does that let me do? That lets me take my partial fraction. So remember, I was trying to find a different way of writing this. And now I have a different way. Up here, notice I have my a right there, but now we know that a is 8/5. So I have 8/5, and that was over the x minus 3. And then I have -3/5 for b. So I'll just put the minus out there, and I have x plus 2 here. Okay, and that's great because now what we could do is we can go back to the integral. So if we go back to the integral, remember we have that x out there that we had earlier. Now instead of writing x plus 5 over x minus 3 times x plus 2 like we did earlier, I'm instead going to write it in this new way. So we have 8/5 over x minus 3 minus 3/5 over x plus 2. Okay. And then now that we're here, now that we have a constant over x plus or minus a number, all of these integrals will end up being natural logs. So if I were to do another step here, moving up, I still have the x there, and then this is a constant. So I'm going to have that on the outside, and then I have my ln of absolute value of x minus 3, and then I have my minus 3/5, and then I'm going to have ln of absolute value of x plus 2 here. And we have plus c. And so that's a basic application of using the partial fraction decomposition, which is really just an algebra technique where we split this into multiple fractions. I could use that to make my integral much easier, and then I can get my answer here. All right, so there's our first example. Now what I want you guys to, well, I'm just so used to saying that. What I would normally have you guys do is do the practice example. And the practice example for this actually uses the second long division that we did. So for my second practice here, which I guess now it's just me doing it, we have the integral of x squared plus 5x plus 6 divided by x squared minus 3x plus 4. Okay, so we have these guys divided together. Now, before doing any of the partial fractions, we need to do long division, because partial fractions only works correctly if this degree is less than this degree down here. But the good news is that earlier we already ended up doing our long division for that. Let's pull that up. See, our long division for this ended up being this right here. So I end up with 1 plus 8x plus 10 over x squared minus 3x minus 4. So I'm just going to copy that into my integral because I already figured out long division for that. 3x minus 4. And then just like before, if we ever get anything in what's called the quotient or the result of the division that's not being divided by the denominator anymore, then we can just integrate this. Usually it's an easy calc 1 integral. So now we have x, and then at this point we could focus on 8x plus 10 over x squared minus 3x. Okay, so now we can do partial fractions on this because the degree of the top is lower than the degree of the bottom. The degree of top is lower than the degree of bottom. We have that satisfied, so now we can do partial fractions. So the first thing we do is we fully factor as much as possible. I guess I could pull a 2 out of the top. That's not essential, I guess, but I'll make things a little better. And then on the bottom here, let's see, we have x squared minus 3x minus 4. If I'm not mistaken, that will factor into x minus 4 times x plus 1. All right, so we fully factored everything. And then now we want to have a coefficient on top of each one of these. So we're going to have one coefficient for x minus 4, and another coefficient over x plus 1. And you may see people use different names for these. I think it's most common to just kind of go through capital letters in the alphabet, but you may also see them be called like C1 or C2 or something like that. But it's all the same. They're all just constants that we don't know yet. All right, so now that we have this, we know we can write our integral like this, and that'll be good because we'll just get 2 easy natural logs for that. But first, we got to figure out what a and b are. So what I'm going to do is I'm going to use cover-up method. So first, I'm going to get a. So for a, my x is going to be 4 for that. So what I'm going to do is I'm going to put 4 into here in every term except for the one that it shares with my coefficient here. So I'm going to have 2 times 4 plus 5 divided by, the only thing on the bottom left is going to be 4 plus 1, which will be 5. All right, what's this number going to be? So we have 16 plus 5 is 21 times 2. So we end up getting 42 over 5 for a. And that's one unfortunate thing about partial fractions. You may end up getting some kind of bizarre fractions in here. It won't matter as much for these cases, but for the later ones, which we'll talk about next class, these can be kind of annoying to deal with. Anyways, let's do B's cover up. LBX equals -1 for that. So I'm going to plug that in. So I have 2 times 4 times -1. That's 5. Then I divide here. Now this time I'm going to include the x minus 4, but I'm going to skip the x plus 1 because, again, that's the one that they share right here. All right. So let's see. We have -4 plus 5 is 1. Times 2 will be 2, and then over -5. A much simpler number for this one ends up being -2/5. So this means that we can rewrite our single rational function here into 2 simpler ones. So we end up with, let's see, our a, that's 42/5 over x minus 4 minus 2/5 over x plus 1. All right, so there's our partial fraction decomposition with the coefficients found. Now let's return to the integral. So that was all just algebra. Let's go back to our integral. Now remember, our integral was this 8x plus 10 over this stuff, but we just found out that it's actually equal to these 2 separate fractions. So we have 42 over 5 divided by x minus 4 minus 2/5 over x plus 1. And then finally, just like last time, I can integrate these both pretty easily. These are just constants, so they just kind of come along for the ride here. Then I end up with ln of absolute value, x minus 4. And then the same thing happens for the next term. And then I have plus c. And there we go. So that's another example of case 1 of partial fractions where we can factor our denominator into distinct linear terms, x plus or minus something, and then x plus or minus a different number. And we could also potentially have 3 of them if our body was cubic, but this will work essentially the same way. Oh my God, the fan's blowing my paper. This will essentially work the same way no matter what, as long as we have just x plus or minus different numbers down here. Okay, now one thing I want to say before we continue, and this is, so probably the most common mistake in Calculus 2 normally would be forgetting your plus C. And that one's not like a huge issue. If you were doing like a free response question in a normal year, that'd be like a -1 point or something. Like it's something you should have there, but it's not the end of the world. If it's not going to totally mess up your answer if you don't have it. I mean, definitely include the plus C. But just a second, let me turn this fan off. There we go. Sorry about that. Yeah, so plus C is usually the most common mistake we make when we're doing all these integrals in Calculus 2. But the second most common mistake, which will probably be the most common for you guys, since plus C will be automatically added into a lot of your answers, is the following. One common misconception we may get from Calc 1 or maybe somewhere else is that the integral of 1 over some kind of function is going to be equal to ln of absolute value of whatever that function is, whatever was down there, plus c. And this is most certainly not true in general. I mean, we might be like, oh, Dr. Manley, you literally just did that. You had x minus 4 on the bottom here, and then you stuck it inside a natural log. So guys like this are actually the exception. So the only time this is true, it's only true when we have the integral of 1 over x plus or minus some number, which I'm just going to call a. In that case, it actually is equal to ln of absolute value of x plus or minus that number. But if this is any different, even if there's like, you just flip these and you have a negative on the x, or if you have an x squared or anything else down there, this is not going to be true. It's only true when we have x by itself or x plus or minus a number. And for a lot of these problems, I'll end up seeing people do the integral of something like 1 over x squared as ln of absolute value of x squared, for example, when we really know the antiderivative of this is -1 over x if we do the power rule. And these are not the same function. So yeah, just remember that in general, the integral of 1 over something isn't just going to be ln of that thing. It's only true if it's just 1, or maybe a constant up here, over x plus or minus a. And it has to be, there has to be nothing in front of this x. That's why I didn't move these 5s down here. I didn't multiply through by those. And it's only true, there's no sign in front of there. It's x to the first power plus or minus a number. This is probably the biggest mistake that people make in this class. This is probably the most common thing that I see go wrong, besides like silly things like omitting plus c. So definitely make sure that you understand this. Now you may be able to, you may end up getting ln as part of your answers. Like you've probably seen this already where we have natural logs in there, but usually that comes after a u substitution where we're able to make f of x be a u. Then it's technically a single variable, and then we can do the integral. But if it's just some crazy combination of variables like in a general function right here, you're not going to be able to do that. So I just want to clear that up right now before we get too far into things. All right, so there's my warning. So now what we're going to do, so we're going to do a partial fraction decomposition. We have degree 3 polynomial on the bottom. And as we'll see, since it's still just distinct linear factors, it's essentially going to be the same as what we've done before. Just have to do a little bit extra work. So let's say we want to integrate 1 over x plus 2 times x minus 1 times x. Let's say we want to do this one. Now this one certainly isn't doable by trig sub because you're going to get some weird cubic thing down there, and that's not going to behave very nicely. Also, just so we can practice using our new rule, or rather not making this mistake, this is not just going to be ln of the bottom down here. So we can't just make it that easy, unfortunately. But what we can do is we could use partial fractions to get at this. Now, for the other examples, we had our numerator have the same degree or bigger than the bottom. But in this case, 1, that counts as a degree 0 polynomial. And down here, we have a degree 3 polynomial. We actually don't need to do any long division here. And even if this were like, I don't know, like an x minus 2 squared or something, we still wouldn't need to do it until the top became cubic or bigger. All right, so we don't need to do long division here. So now we could just jump straight to the partial fractions. And it's even better because this is already factored for us. So we don't need to worry about factoring that cubic. All right, so we have our a, that'll be over the x plus 2. We have our b, that'll be over x minus 1. And then we have our c, which will be over x. And notice how each of these terms is distinct from one another. We don't have 2 x minus 1s or anything like that. And then the nice thing is we could just do cover up for each one of these guys. So move this up a little bit. So for example, for a right here, the number we're going to plug in for a will end up being -2. So we're going to do x is -2 for that. And my a will end up being 1. Let's see, we're not going to have this term because that's the one it shares over here. We're going to have -2 minus 1 will be -3. And then we have just x itself, which is -2. So when all is said and done, our a is 1/6. And then we can do the same thing for the other terms here. So this time I'm going to plug in 1 because that's what makes this 0. I have 1 over 1 plus 2 will be 3. I skip this one because it makes the bottom 0. And I have a 1 here. So I end up with 1/3 for b. And then finally for c, x equals 0 is what makes the bottom of this 0. So that means that over here, we're going to have 1 over 0 plus 2, and then 1 over 0 minus 1. So we have -1/2 for that one. All right, so we got all 3 of our coefficients using the cover-up method, which is good. That means we're ready to turn this integral here into 3 separate terms like this. So we have our 1/6 over x plus 2, and then we have 1/3 over x minus 1. And then finally, we have -1/2 over x. And all of these do fall into the category where it's just x plus or minus some number on the bottom. Or if a is 0, it's just x. So these will turn into natural logs. We have 1/6 ln of absolute value of x plus 2 plus 1/3 ln of absolute value of x minus 1, and then -1/2 ln of absolute value of x. And then we have plus c. So as you can see here, as long as we have distinct linear factors, having more of these isn't really that big of a deal. It just means we need to do cover up one more time. The integrals will all be just as easy for these. All right, so that takes care of case one where we have distinct linear factors. So let's talk about case two for partial fractions. Case two is where we have some repeated linear factors. So what do I mean by that? Well, let's take a look at an example. Let's say we have the integral of 1 over x plus 2 quantities squared times x. Okay, so again, this looks like something maybe we could use partial fractions on because it's some rational function. So what we're going to do is we're going to use partial fractions here. But the difference between this and the previous examples is that I have this x plus 2 times, because technically, of course, this is going to be the same as 1 over x plus 2 times x plus 2 times x. Hence the word repeated. We have some of these factors more than once, and we group them together in a power. Okay, well, let's do partial fractions. We have 1 over x plus 2 squared times x. Now, remember what I said earlier. I'm going to keep saying this over and over again. The degree of my denominator polynomial is going to be the number of coefficients that I end up having. So if I were to FOIL all of this out, I would get an x squared from this times an x. That means I'm going to get an x cubed from this. So I'm actually going to have 3 coefficients here. Now, I think it might be kind of clear what 2 of them might be. Well, we have an x down there, so I guess we can have an x. We have an x plus 2 squared, so we'll probably have something like that. But then the thing is, we need to have a term for this for each power lower than this as well. So I have one for x plus 2 squared, and I'm also going to have one for x plus 2 to the first power, or just this without any powers. And if, say, for example, I had an x plus 2 cubed in here, then I would have one for each power, starting at 3, then I have a 2, and then I would have 1, meaning I would have 4 coefficients in that case. So you need 1 coefficient for each copy of your repeated factor. So we have x plus 2 squared, and then we have x plus 2. You'll find that if maybe we had like just an x plus 2 and an x plus 2, you could try that on your own. You'll see that the partial fractions, you won't actually be able to get it to work out in that case. You need to have these be different powers. All right, now the good news is the cover-up method is easy, right? And we can still do cover-up, but we can't do it to get all of them. So you can only use cover-up. So cover-up only works for the highest powered term. What does that mean? Well, since there's only one x here, this is by default the highest power, so I can get the a here. I can get the b here because this is the highest power of x plus 2 I have, but I actually can't use cover-up to get c. So I need to figure out a different way to get c, but why don't we at least get the ones we know how to get right now? So for my a, for that one I use x equals 0. So I have 1 over this, but then I ignore the x. So it's 1 over 2 squared, which will be 1/4. Okay, that's A. We can definitely get B. So we have B with x equals -2. And that's going to end up being equal to, now what we do for this one is we get rid of all of the terms right here. So we get rid of everything with an x plus 2. And then we end up just with 1 over x, which will be -1/2. Now for C here, the reason why we can't do cover up for this is that normally we would cover up in our big function over here exactly what we have down here. So in this case, we would end up trying to cover up just a single x plus 2, but the problem is that we would still have another x plus 2 down there, and if we plugged in -2, we'd be dividing by 0. So that's why we can't use cover up for this one. Now what we can do, so our sort of backup for cover up is by plugging in numbers. Okay, so let me explain how this is going to work. So up here, let's see here. Up here, This is actually an equation of rational functions. What I'm saying is for any x I want, this rational function should be the same as this rational function. Now, that means that I could plug in any number I want for x, and this will still be true. Now, I already plugged in x equals 0 and -2. Technically, that's really how I got a and b. So all I need to do is plug in a number that's not one of these into everything in here, and then I could solve for my c. Now, typically, I like to do 0 for this. 0 is probably the most convenient number to pick for these, but we already use 0 technically. You can't use any numbers you use for cover-up. So I don't know. I guess it's kind of up to you what you want to pick. I'm just going to pick x equals 1. I don't think that's going to be a hard number to plug in. So if I plug this into my entire equation here, I have 1 over 1 plus 2 squared, which will be 9 times 1. So remember, I'm plugging 1 into this and then all this. And then I have a over 1. Then I have b. And then if I plug 1 in here, 1 plus 2 is 3, and squared will be 9. And then I have c over 3. Now the thing is this equation has 3 variables, but we actually already know what 2 of them are. So we can change this equation to be 1/9 is going to be our a, which is 1/4, plus b, but b is -1/2, so we have minus 1/18 when we plug -1/2 in for that. And then we have our missing number, which is c over 3. All right, and then now you see we just have a little bit of an algebra problem here to get what c is going to be. So the first thing I'm going to do is I'm going to try to clear the denominators here. Let's see. I think if I multiply both sides by, I think 36 would be the least common multiple of these. I just want to get rid of all the fractions because they're kind of annoying. I'm going to multiply this whole thing by 36. But you could play around with the fractions. You don't need to do this if you want. It just makes it easier. So 36 over 9 is 4. 36 over 4 is 9. 36 over 18 is 2. And then 36 over 3 is 12. Let's see. All right, so then I'm going to add 2 and subtract 9, which is the same as subtracting 7. So we end up with -3 is 12c. And so we end up with -1/4 being our c. So it took a little bit of extra work to get c, but that's just the price we have to pay if we want to use this on repeated factors. But the good news is that we have all 3 of our coefficients now, so now we can use this instead of the original rational function. Alrighty, so let's see how this is going to go. So our original integral, which was the old rational function, will now turn into this right here. So first I have a over x, but a was 1/4. So I have 1/4 over x. Next I have b over x plus 2 squared, and b was -1/2. So I have minus, and then I have a half. Then I have x plus 2 squared here. And then we just figure out that c was -1/4, minus 1/4. That's over x plus 2 to the first power. All right, so now we're going to integrate this, but the thing is that, so we know how to integrate these guys. We've been doing this all day now. These are just going to be natural logs. But this one right here will be a bit different. So let's see how this is going to go. All right, so this one's going to be 1/4 ln of absolute value of x. That's no surprise. This one's going to be minus 1/4 ln of absolute value of x plus 2. Okay, so we took care of these two. Now this one down here, whenever we have x plus or minus something raised to a power, we can almost treat this as if it's one variable. And another way of thinking about this is I could do like a little mini u sub with u equals x plus 2. My du would just be dx, so I effectively just make this one variable, and then I would do the power rule here. So one thing I like to do to save time is when I have just x plus or minus a number, remember nothing can be here, it can't be a different power, etc. I just use the power rule on this, and that's totally fine. So this is x plus 2 to the -2nd power. I raise that power by 1 to be -1, and then I divide by the new power, so divide by -1, making that be positive. So when the dust settles here, I have 1/2, and then I now have it to the -1st power. That's raising the power by 1. And then we have plus c. Now, if you don't feel comfortable doing that, you could always feel free to do a little u sub down here, u equals x plus 2, but at the end of the day, you'll end up getting the same thing. So to recap, both of these were just our typical log examples here, and then this one I use the power rule on, and I can do that when we have x plus or minus a number. This negative second power raised to be the negative first power, and I divided by that, which is why this became positive, and then now I have that to the negative first power, that 1/2. Finally, another way we can simplify this, we couldn't really do this easily with the other ones because they were all different coefficients, but technically these guys right here have the same coefficient. Now, it may have been a while since you've done your log rules, but remember, if we subtract logs, log of something minus log of something else, it turns into division on the inside. So another way you might see this written would be 1/4 ln of x divided by x plus 2. And then we still have this term. So this might be another way you can see it. And if we really wanted to as well, remember the coefficients on the outside of a log, those can turn into a power. So another way of reading this is ln of the 4th root, or the 1/4 power, of all of this stuff. So we can move the power in there as well if we want to. All right, so that's how we deal with that one here. And all right, that looks to be about it. So there's our case 2 example. But in general, the only difference between this case 2 and case 1 is that we need to plug in a number to get what the lower powers of our repeated factor end up being. We just have to plug in a number. You can plug in any number you want, but I recommend picking like small whole numbers or 0 if possible. We couldn't pick it here. And then our integral will mostly be the same, except if we have something squared on the bottom and it's x plus or minus that, we're going to do the power rule to get this right here. Finally, one thing I want to mention, because I think I forgot to say it last class, but it'll end up coming up quite a bit. So in addition to memorizing the integral of secant cubed, another thing I want you guys to take a look at is the integral of 1 over a squared plus x squared dx. So this is an integral where this is some number and we square it, but really you just think of a as the square root of whatever this number is. This is an integral that shows up actually definitely more often than secant cubed. So it's also worth knowing the integral of this as well. And it's going to end up being 1 over a times arctan of x divided by whatever this a is. And the way we would get this is we would do a little bit of a trig sum. We would have x is a tangent of theta, because we're adding these together. Dx would be a secant squared, and then our integral would turn into a secant squared of theta d theta, and our bottom would be a squared plus a squared tangent squared of theta. So we would have some a's cancel out, and that's where we're going to get our 1 over a from, because we have an a squared down here, but an a the first power up here, and then we have secant squared of theta divided by 1 plus tangent squared of theta. But as we know now from doing trig sub, 1 plus tangent squared of theta is the same thing as secant squared. These guys technically cancel out, and we're actually just integrating 1 for this. So we have 1 over a, and then the integral of 1 will just be theta. But remember, if we solve this for theta, x over a is tangent, and we do arctan of both sides, our theta is going to be arctan. So we end up with what I said up here. Okay. Now, rather than doing that every single time, rather than doing a trig sub every time you see this, I encourage you to just kind of jump the gun here and just skip to this part. Now, this only works if there's no intermediate term here and there's nothing on top. It's just all of this stuff right here. But this integral shows up very often. So I recommend memorizing this. It'll definitely save you a lot of time. I think I forgot to mention that last class. All right, well, that's all I have to say right now. Hopefully you guys get a chance to watch this over the weekend, and then we'll learn more about partial fractions coming up on Monday, where we'll see 2 other cases of rational functions. I'm also going to post the notes from Wednesday's class and this class right here. I'm going to fill out a worksheet with all of this stuff too, so you guys can take a look at that. All right. Well, that's about all I have to say. So I will see you guys on Monday.